Good morning, my dear students. Welcome to the GPS class. So, how are you doing all? So, as per our curriculum, I will revise the unit 4 and as well as the unit 5 also. And from your side, is there any specific topic needed to be revised once again? If it is there, please type in the chat box. If not, you find enough time and message me. Okay. I hope my internet connection is good enough. Okay, now let me share the presentation of the today's revision class, that is unit 4. So here it is. We'll start from the beginning. I think from this many questions have appeared in the mid-2 exam. So this is the outline, that is contents, and the title of the unit is differential GPS or differential GNSS. Of course, Global Navigation Satellite System is the main origin name, and the two constellations among the GNSS system are, one is the GPS and there is the GLONASS. Of course, the third one is also there, that is called as the Galileo. Each country have developed their own constellations. Depending on that, the names were given. And the first and foremost of the GNSS system constellations is, as we already knew, that is the GPS, Global Positioning System, which was developed by US government, Department of Defense, DoD. Of course, from the Department of Defense, so many inventions have come, including your Verilog HDL, including the EHDL, that is Verilog HDL, and VHDL, hardware description languages, which you might have learned in your previous standards, right? So in this unit, we have to learn about the topics like local area differential GPS. So first, give a concept of differential GPS, then local area types of differential GPS. Local area differential GPS, wide area differential GPS. Of course, the differential GPS concept is a kind of augmentation of the GPS system. Is a kind of augmentation of the GPS system. Augmentation is nothing but the improvement of the accuracy, improvement of the precision values, and removing the errors to the possible extent, to be more accurate, to be more precise, and to be more reliable. So these are the improvements that are required by a navigation message output at the end. So in our conventional GPS or the normal GPS, this augmentation is not developed. Hence, there were some errors. There were some errors introduced in the system of navigation. Then these systems are to be wisely removed. The systems are to be wisely removed from the navigation output message. For that purpose, the conventional GPS is not only enough. The conventional GPS is not only enough. We need to add some extra features to that. That include mostly the reference stations. So we have learnt about the pseudo range measurements and the pseudo phase measurements in our conventional GPS. Now, in addition to that, we are using some local transmitters. We are using some local transmitters where they are placed in the reference station. Yes, I'm sorry, I have unmuted. So here, the purpose of the taking a known location is we are applying our all navigation principles and we are giving the output of the position of a reference station. And the reference station's location is already known to us. Now the known location and calculated location both are compared, and if at all there is any mismatch, then we conclude that the calculated location is erroneous, and that is due to some errors which are induced. That may be due to ionospheric error, maybe due to clock error, or maybe due to the tropospheric error, or maybe due to the tropospheric error. So because of these errors, some errors are introduced, and these errors are forwarded to the actual GPS user. This much error is there due to ionosphere, this much error is due to the troposphere, this much error is due to the clock error. These all calculations will be done, and these will be sent to the actual user which is present at the master station. And then after calculating the user position by the user, then he will apply those corrections which are sent by the receiver. And this is the process of augmentation. This is the process of augmentation. Augmentation is a way of improvement in the calculations. Augmentation is a way of improving the accuracy. Augmentation is a way of removing the errors. Augmentation is a way of improving the precision. Augmentation is a way of providing the reliable corrections. And for this purpose, what are we using is the differential GPS. We are using the concept of differential GPS. And there are different types of differential GPS that include local area differential GPS, wide area differential GPS, space-based augmentation system, ground-based augmentation system, and LORAN-C. Of course, this is in the concept of differential GPS. We are using a geostationary satellites. We are using geostationary satellites for the uplink and downlink. Of the data from the master station to the actual user, and from the actual user to the master station. We are using the geostationary satellites. And there we have to develop the systems, like whenever there is a satellite connectivity is there, satellite connectivity is established by developing a uplink system and also a downlink system. And we have to determine the orbit properly. So there we will study the orbit determination, geo-orbit determination. And in that we have two things, geometric analysis and covariance analysis. And finally, the GPS is using a reference. So which reference it is using? It is using a RF signal. Of course, we know the conventional trilateration technique. In the trilateration technique of GPS navigation, what will be done? So a signal, RF signal will be sent from the satellite. Of course, not only single satellite, from 3 or 4 satellites, minimum 4 satellites is enough. And the signal travels time is calculated by using the clock, which are synced with the UTC, and that time into the speed or velocity of the RF signal. Of course, the RF signal travels with the speed of the light. So speed of the light is taken as the reference here, and it will be multiplied with the time of travel. Then we will be able to calculate the distance. And if we know the distance of the user from 3 of the satellites, then it is easy to find out the position of the user. Easy to find the position of the user. So it is what is called as the trilateration technique. Of course, recently we have revised this. So how trilateration is done, you can refer my previous videos. So what is differential GPS? Of course, till now whatever I spoke, it will be presented here. What is differential GPS? It is a technique for reducing the error in the GPS derived positions. It is a technique for reducing the error in the GPS derived positions by using additional data from a reference GPS receiver at a known position. Right? And the most common form of differential GPS involves determining the combined effects of navigation message ephemeris and satellite clock errors, including the effects of propagation at a reference station, and transmitting the delay corrections in real time to a user's receiver. See how beauty the augmentation system is. So we are transmitting the delay corrections in real time to the original user's receiver. It is not the post processing. And how do we know the corrections? Because we have taken a known reference station. Because it is a known reference station, after applying the GPS principles and navigating it, we will be able to conclude the errors. And what kind of errors will be taken into account by the differential GPS is there is a limitation. Of course, there are many errors which you have studied, and among them, selective availability error, satellite ephemeris and clock error, ionospheric delay error, and tropospheric delay error. These 4 errors will be accounted. These 4 errors will be corrected. Selective availability if present, because selective availability is a feature which is removed, right? If present, it will be taken into account. If absent, that will not be accounted for. And satellite ephemeris error, satellite clock error, ionospheric delay error, and tropospheric delay error, and which are not covered under the differential GPS. Which errors sources are not covered under the differential GPS. That is also important for us. So one is the multipath error. This is not covered. And user-induced errors. Intentionally, users will induce some errors into our GPS system. They are not covered. Because those errors, user-induced errors, user will induce errors into the user, not to the reference session. And reference session doesn't know this information that there is an error induced by the user. And also the multipath error. Multipath error is after it is falling on the ground. When it is falling on the ground, not directly on the intended user, then it may fall on some other metallic surface, and it will reflect back, and it may take another path and finally reach the user. And this may not be the case with the reference session. Hence, the multipath error and user-induced errors are not covered in the differential GPS. Of course, they are accounting for a very less value that may be denied by the user himself. So is this clear, guys? Any doubts till now? If you have any doubts, you can Write in the chat box. Okay. Right. Now we'll proceed. So this is local area differential GPS. Of course, the wide area differential GPS and local area differential GPS, they differ only in the geographical area that they cover. The local area means a limited area. Wide area means over a large area. So what is LAT GPS? LAT GPS is a form of DGPS in which the user's GPS receiver receives the real-time pseudo range and carrier phase corrections from a reference receiver located within the line of sight. Located within the line of sight. It is not far away. From the user, the reference station are at line of sight propagation. At a line of sight propagation. They are not at a far distance. So that is called as the local area differential GPS. And the corrections account for the combined effects of navigation message ephemeris and satellite clock errors and atmospheric propagation delay errors at the reference station. Of course, this topic we already knew just now. And with the assumption that these errors are also common to the measurements made by the user's receiver, the application of the corrections will result in more accurate coordinates. So finally, ultimately, what are we doing in our navigation process? We are giving the coordinates. We are giving the coordinates of the user, x coordinate and y coordinates, of course, latitudes and longitudes. So we are exactly locating the user receiver where it is present. And these corrections are applied to the reference station. These corrections are applied to the reference station. And same corrections are applied to the user. So that we will get a more accurate coordinates. So that we will get a more accurate coordinates. Right. And the next one is the wide area differential GPS. Wide area differential GPS. So it is a form of differential GPS in which the user's GPS receiver receives the corrections determined from a network of reference stations. Underline this word. From a network of reference stations distributed over a wide geographic area. So it is not line of sight reference station. The reference station is not in the line of sight. It is a network of references. It's not even a single reference station. It is a network of reference stations. That means there are many reference stations which are distributed over a wide geographic area. Which are distributed over a wide geographic area. And separate corrections are determined for specific error sources like satellite clock errors, separate corrections, ionospheric propagation delay, separate corrections, and ephemeris data errors, separate corrections. The corrections are applied to the user's receiver are attached to a computer in computing the receiver's coordinates. So these may be applied to the user's receiver. If not, here we are doing the post processing, or they may be attached to a computer where the computing of the user's receiver coordinates are done. While calculating the receiver's coordinates in a computer, if these corrections are applied, then it will give the accurate measurements. May not be directly given to the user. Getting it? Any doubts till now? Okay. Now, here we are knowing the importance of the geostationary satellite. Now these corrections are done, but our user is at a height, altitude, that is aeroplane. Mostly this is applied in the aeroplanes. And how this is sent? Here we take the advantage of the geostationary communication satellite. And these corrections are supplied in real time by way of geostationary communication satellite or through a network of ground-based transmitters. Of course, ground-based transmitters will cost more. Instead of that, we will use a satellite because satellite systems are already developed and that may be used for this purpose. And corrections may also be provided at a later date for post-processing the collected data. Of course, here we will we may take the advantage of the post-processing. We may take the advantage of the post-processing. And this is satellite navigation's space-based augmentation and ground-based augmentation implementation. Of course, this is WAS, wide area augmentation system, will come under space-based augmentation system, and LAS is the local area augmentation system, will come under the ground-based augmentation system. So in the transmission of the aeroplane, there will be terms like en route, terminal, and approach. En route, terminal, and approach. En route may be done in the oceanic area. En route may be done for the domestic, and terminal is I think 2.5 nautical miles from the landing airport. This is called this. So here departure, and here approach. Of course, here two types of approaches. One is the precision approach, and another one is the non-precision approach. So here this is a non-precision approach, and here this approach is missed here. Then we will apply the corrections. So category 1 approach, precision approach, and category 2 and category 3 may be done. And finally to the landing. On the surface it will be landed. And from terminal to the landing, this is called as the local area augmentation system. And above this, this is called as the wide area augmentation system. Wide area augmentation system. This picture gives you more information. Please make a note of this. Right. So here, augmentation systems include space-based augmentation system and ground-based augmentation system. And space-based augmentation system, we have one system that is called as the wide area augmentation system. Wide area augmentation system. So what WAS will do? WAS will enhance the GPS SPS and is available over a wide geographic area. Of course, the WAS was developed by Federal Aviation Administration, of course, together with some another agencies, allied agencies. What it will provide? It will provide the WAD GPS corrections, additional ranging signals from geosatellite, and integrity data on the GPS and geosatellites. See, WAS is doing some additional things. That is, it will provide the WAD GPS correction. Of course, it has to do additional ranging signals from the geosatellites and integrity data on the GPS and geosatellites. So there should be some integration between the GPS satellite and geosatellite. Here, two types of satellites are there, and that data also will be transmitted by the WAS communication system, WAS augmentation system. And each geo uplink subsystem includes a closed loop control algorithm and special signal generator hardware. Of course, here we will use some special hardware. We'll use some special signal generator hardware and also a closed loop control algorithm. For what? For providing the WAS corrections. And these will ensure that the downlink signal to the users is controlled adequately to be used as a ranging source to supplement the GPS satellites in view. So what is the advantage of this hardware generator? Is it will downlink the signal to the users. It is controlled adequately so that if there is any ranging we are doing, and that is which is supplement to the GPS. Actually, we are using a GPS satellite for range calculation, and from geostationary satellite also the same type of signal is received by the user. So this may supplement that. And it is a WAS diagram, original, of course, a typical diagram. So this is these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reference stations. This is actual GPS user. This is a communication satellite. 1, 2, 3 are the GPS satellites. 1, 2, 3 are the GPS satellites. Of course, these three satellites will send the RF signals to the user. RF signals to the user. And of course, the same signals are received by the reference stations. Reference station 1, 2, reference station 3, reference station 4. And the calculation of the GPS navigation is done here of the same signals, and correction and GPS navigation calculation is done by the user also. And these are with known locations. This is with a unknown location, which is to be navigated. Now, if the if the calculated values are not matching with the known locations, then that much of correction is there. And how this information is transmitted to the reference station is, first it will send it to the ground earth station. This will send it to the ground earth station, and ground earth station will transmit it via uplink system to the communications satellite. And the communication satellite, from there it will transmit to the user. Then he may apply the corrections. There itself. Of course, one more concept also we have learned here. Of course, here there will be a master control station. INMCC, Indian National Master Control Station, in our Indian Gagan system. And after post-processing, after calculating the user's position, while calculating the user's position, if these corrections are applied, then the accurate position may be known. Any doubts in this? If no doubts, we'll proceed. Yes. So this is a typical block diagram of a wide area augmentation system, which is a part of space-based augmentation system. So some historical truths about this. The primary mission of WAAS is to provide a means for air navigation for all phases of flight in the National Airspace System, NAS, from departure, en route, arrival, and approach. There are 4 phases we said, right? Departure, en route, arrival, and approach. Approach is actual landing. Departure is where it is taking off. The flight is taking off. En route is where it is traveling in the air through ocean or through the some hilly areas, whatever it is. And after that, the next step is the arrival. Arrival means it is just 2 nautical miles away. In the air, the distance is calculated in the nautical miles, 2 nautical miles away from the landing position. And finally to the approach. Approach is just 100 meters or 1 kilometer away from the landing airport. And the GPS augmented by the WAAS will offer the capability for both non-precision approach and also the precision approach within a specific service volume. Within a specific service volume, it will provide the corrections for both the approaches. Of course, these are the 2 approaches which are used by the aviation people. One is the precision approach and another one is the non-precision approach. Whichever the approach used by the aviation people, the corrections may be wisely applied by the WAAS system. And this is primary task. And the secondary mission of the WAAS is to provide a WAAS network time offset between the WAAS network time and UTC for non-navigation users. So there are some other non-navigation users, like some scientific applications. They don't need the navigation, but they need some presence of the metals below the underground, right? And for that purposes, there should be a time offset between UTC and WAAS network time. WAAS network time is different and UTC different. So there is always an offset which will always change. And that offset is provided by the WAAS. And WAAS provides improved en route navigation and precision approach capability to the WAAS certified avionics. So only to the WAAS certified avionics, of course, improved en route navigation and precision approach capability. And the safety critical WAAS system consists of the equipment and software necessary to augment the Department of Defense provided GPS SPS only to the authorized users, which are nothing but the Department of Defense provided GPS users. And WAAS provides a SIS, signal in service, to WAAS certified aircraft avionics using the WAAS for FAA approved phase of flight. So what is SIS? SIS provides two services. One is data on GPS and geosatellites, as we already learned. Data on GPS and geosatellites, and ranging capability, and also the ranging capability. Then the GPS satellite data is received and processed at widely dispersed wide area reference stations, that is WRS, which are of course strategically located to provide a coverage over the required vast service volume. And these data are forwarded to the wide area master stations, which process the data from multiple wide area reference stations to determine the integrity, differential corrections, and residual errors for each monitored satellite and for each predetermined ionospheric grid point. IGP is ionospheric grid point. Of course, how much error is caused due to the ionosphere is known by this IGP. Of course, this all we already learned this. And the local transmission between the WRS wide area reference station to the wide area master station is done using a terrestrial communication subsystem. Mostly we use the optical fiber communication system. And the information from the wide area master station is sent to the geo uplink subsystem and uplinked along with the geo navigation message to the geosat. Of course, this all we have just now viewed in the diagram. And the geosatellite downlink these data to the users via GPS SPS L band, that is ranging from L1 frequency with the GPS type modulation, that is BPSK, biphase modulation system. Of course, this is another diagram of the VAS. This is a VAS receiver, wide area reference station WRS1, WRSN. There will be a number of, and it is a wide area master station, and this is a uplink system. This will be given to uplink system. Uplink system will give it to the geosatellite, and geosatellite will give to the user receiver. And here are the GPS satellites. Here are 4. Right. Of course, subsystems of VAS, functional verification, correction and verification we have learned. And C&V has 11 capabilities. Just name them. Control C&V operations and maintenance, COM. Control C&V modes, monitor C&V, MCV, precise input data, satellite orbit determination, ionospheric correction computation, satellite correction processing, independent data verification, message output processing, C&V playback, and integrity data monitoring. Integrity data monitoring. And of course, in the background, there are algorithms for the WMS, and independent data verification and validation algorithms are also present. Of course, these all will improve the quality of the VAS. And IGNOS is there. Of course, the time is already 11:20. We'll study that in tomorrow's class. Till now, any doubts, guys? Thank you for today's class.